welcome back. This is Unit 9.2, and in this section of Unit 9, we're going to be talking about the heating curve. Specifically, the heating curve for water is what we're going to concentrate on. This is pages 597 through 600 in your book, and 248 through 263 in your workbook. So the heating curve. Well, we're going to concentrate on the entire heating curve, but for this screen, we're just going to look at the heating curve for water, the lower end. And what I mean by that is negative 10 degrees up to 50 degrees or 35 degrees, whatever. So the heating curve of water has two areas that flatten out. So let's look at this graph and let me explain what's happening here. Well, it starts off at negative 10 degrees here. And we can see the y-axis here is temperature and the x-axis is the amount of heat that's being added. So here, this sloped area from negative 10 degrees up to 0 degrees, this point right here, for water, that's when water is a solid, and we call solid water ice. So this section here is where we have ice. And as we add heat to ice, the temperature of this ice is going to increase. So that's why we have this positive slope here. And it's going to keep absorbing this heat energy until it reaches 0 degrees Celsius. Now, as with water, solid water at 0 degrees Celsius, something starts happening. This is going to start actually melting. So here it's not melting, it's just absorbing heat. But once it hits 0 degrees Celsius, water is going to start melting and going through a phase change. Now, the graph that flattens out here, we see is at 0 degrees. So we're still adding heat and time is still ticking away, but the temperature is not increasing. That's because all of this heat energy that you're adding now is going to break the bonds from this water molecule to this water molecule. There's a little bond right here. This heat, this energy is going into breaking that bond there to separate these two molecules a little bit so they change into the liquid form. So this is going to stay at 0 degrees until every sliver of ice has been melted. When the last two molecules that make this solid ice, once they break apart, then this heat energy that we're adding is going to start increasing the temperature of the water. Now this is ice, which is a solid. This right here, this slope is liquid. This is the liquid phase of water. So here we have the solid absorbing energy. It gets to this point, it's going to stay the same temperature until all of the ice now has been melted. Once that happens, then it's going to start increasing in temperature again. Okay, so there's no temperature change during a phase change. So this phase change right here has two names, and it depends on which way you're going. If you're adding energy, we're going this way on the graph. Okay, and this is the heat of fusion going this way. If we're traveling down this way, if we're removing energy, like we're taking liquid water and we're making it ice or solid, this way is called the heat of solidification because you're trying to get that liquid into a solid, heat of solidification. Now this number, the heat of fusion and the heat of solidification, are exactly the same number. It's just the positive or the negative of that number. Okay, if we're adding heat, the heat of fusion, if we're adding heat, it's going to be a positive number. If we're removing heat, negative, removing heat, it's going to be solidification. It's going to be the negative of that number. So it's just taking that number really and multiplying it by a -1 or multiplying it by a +1 to change the sign. That's all we're doing there. All right, so this is just the lower end of the heating curve for water. There's also an upper end because as we continue to heat this water, It's going to gain energy. It's going to increase in temperature till it hits this point now at 100 degrees Celsius. And at 100 degrees Celsius, now it's going to start phase changing from a liquid to a gas. We call this water vapor or steam. So when it hits this temperature of 100, then it's going to stay this temperature until every single water molecule that has this bond here, keeping it as a liquid form, this bond breaks now or gets further apart so that it's in the gas form. It actually does break. So it's going to maintain this 100-degree temperature until every last liquid molecule bond has been broken, so now that it's all gas. Now, this point at the top end, we're going to see this graph in just a minute. This whole thing is called the heat of vaporization. If you're going this way toward the vapor, gas, vapor, it's going to be a positive number because we're adding energy. And the heat of condensation is when we're going down this graph, going from a gas to a liquid, because we know that when water condenses, it's going from a gas to a liquid. When water condenses, condensation. And again, this is just the positive and the negative of the same number. So if we were to look at this graph together, both ends, it's going to look, let me find it, something like this. All right, and let me pull this down just a little bit. So here we have point A, where it's negative 10 degrees, so this is ice. Once it hits 0 degrees, it's going to level out until all of the ice is melted. Then it's going to start increasing temperature again. It's going to increase until it hits 100. Once it hits 100, it's going to flatten out again until all of the energy absorbed takes every last molecule to a gas, which is point E, and then it's going to increase in temperature as it's a gas. So this is the complete heating curve of water, and this is just of water. Every single substance has a heating curve, which this area here, B to C, may be longer. This C to D may be shorter or may be longer. This is the particular heating curve for water. So for water, the longest span of time is between D and E. This is where the most energy is absorbed to take liquid to gas. All right, so I'm going to go back a couple of slides here, and we're going to talk about the formula. All right, so this is a little bit different formula that we're using during the flat parts of the graph, during a phase change. So just to review, the formula that we're using is Q is equal to MC delta T, remember? Where this is calculating how much energy is required for a certain phase. So we were just concentrating on the liquid phase of water. So this is how you calculate the energy for this liquid phase, or it could be a solid phase or the gas phase. But when we are calculating the amount of energy during the flat part of the graph, the area where it's phase changing, going from a liquid to a solid or a solid to a liquid, it's a different formula. And that's delta H times the number of moles or grams. It depends on the unit that you have for your delta H. Okay, so it depends on the constant that's given for delta H. These units must match. So if the delta H is given to you in grams, energy per grams, then you use grams. If it's given to you in moles, then you have to make sure you have moles. So we might have to be doing some converting between grams and moles. So for example, how much energy is required to condense? Okay, so we're going this way on the graph. We're condensing. Okay, so we're removing energy. So this is going to be a negative number here. So you see the negative sign there. 20 grams of water vapor at 100 degrees Celsius. All right, so it's at 100 degrees Celsius. So that's when water phase changes from a gas to a liquid. So we're just talking about this flat area of the graph up here at 100 degrees Celsius. So it's asking how much energy is required for 20 grams. So we have 20 grams, okay? And then we're going to multiply that by the delta H value. Okay, so 20 grams times, and this is negative 2260 joules per 1 gram. So for every gram of water, it takes this amount of joules. So we're multiplying those. So here you see that grams cancels grams, and it's just going to leave joules. So this is the amount of energy. Okay, so if we go to our calculator, it's 2260 times the 20 grams. So it's going to take 45,200 joules of energy. So 45,200 joules of energy to remove that. That's a negative. We're removing this much energy in order to take 20 grams of gas or water vapor to liquid. We have to remove this much energy. Okay, so that's just that flat area. Okay, and let's do one where it's kilojoules per mole. So it doesn't always have to be joules. It can be kilojoules. So watch out for that, because we're going to have to convert from joules to kilojoules. How much energy in joules? See, in joules, but it's given us this in kilojoules. So we're going to have to do a conversion between kilojoules and joules. And let's review that. How much energy in joules is required to vaporize 20 grams of water? So now we're going to vapor. Okay, so we're trying to vaporize 20 grams of water. Okay, at 100 degrees Celsius. And so it tells us that that happens at 100 degrees Celsius. And the heat of vaporization, delta H vaporization, is 40.7 kilojoules per mole. Okay, so we're going to take our delta H, which is 40.7 kilojoules per 1 mole. Okay, we're going to multiply this by, we have to multiply it by moles, because this is in moles, but we're given 20 grams. So that tells me I'm going to have to do a conversion. So I have 20 grams, and this is water, 20 grams of water. Okay, and I need to convert that to moles. So I'm going to put grams of water on the bottom and moles on the top, because that's what I'm converting to. So 1 mole of water is how many grams? Well, it's H2O. So there's 2 hydrogens and 1 oxygen. Each hydrogen is 1.01. Each oxygen is 16.00. So that's 18.01. 2, sorry. Because 2 times 1.01 is 2.02. And this is 16 times 1 is 16. So it's 18.02. Okay, so 18.02. Grams cancels, leaving us moles of water. So we're going to take our 20 divided by 18.02. So 20 divided by 18.02. That's going to be 1.1098. All right, moles of water. All right, so now that we have it in moles, that matches this moles, we can put that up here. Moles over 1. Okay, moles cancels moles, and this is going to give us our answer in kilojoules. All right, so all we're doing is multiplying these together, making sure that they're in the proper units. So we're going to multiply that 40.07. Okay, so we're going to take this answer and multiply it by 40.7. That's going to give us 45.1720. Okay, so 45.1720 kilojoules. But it's asking how many joules. So we have to do another conversion. So I'm going to go ahead and I'm going to erase this. So I'll have room to work to do another conversion. All right. So 45.1720 kilojoules over 1. All right. And so it's just the same conversion we've been doing all year long. What unit do we want to get rid of? Kilojoules. So I'm going to put it on bottom to force it to cancel. And I'm going to put joules on top because that's what I want to convert it to for my answer. And there is a conversion from kilojoules to joules. There are 1,000 joules in 1 kilojoule. Because remember, King Henry died by base drinking chocolate milk. So kilo is 1,000 times your base. So 1,000 joules in a kilojoule. All right, so my kilojoules cancels, and so I'm just going to multiply this by 1,000. So all I have to do is move the decimal place over 3 times, 1 place for each 0. 1, 2, 3. Okay, so that's going to be 45,172 joules of energy required to do that. Okay, we're adding because we're vaporization, we're vaporizing. So we're going to add this much energy to get this to go from a liquid to a gas. All right. All right, so now looking at the heating curve. So typically in questions that you're going to see for this section, it's going to give you a range of temperatures that you need to calculate a energy for. For example, it may say that you have water at negative 10 degrees and the final temperature is 50 degrees Celsius. So we're going to have to calculate this section from A to B because water has a different specific heat when it's ice. So we're going to have to calculate this segment of the heating curve. Then we'll have to calculate this segment of the heating curve. Then we'll have to calculate this segment of the heating curve up to 50 degrees. So it'd be up to right here. So we're going to have to do 3 calculations and then add those 3 calculations together to get the total amount of heat. Okay, so let's look at an example problem. It says how much energy in joules is required to heat 20 grams of water from negative 10 degrees Celsius to 120 degrees Celsius. Okay, so let's look at that. So it's a negative 10 to 120. So I'm going to go back and I'm going to look at my graph here. So my graph goes from negative 10 right here up to 120, which is right here. So how many calculations am I going to have to do? Well, I'm going to have to do a calculation from negative 10 to 0, then 1 calculation from B to C, from 0, from when it's starting to turn from a solid to a liquid. So this calculation from B to C. Then I'm going to have to calculate C to D. Then I'm going to have to calculate D to E, and then E up to this point at 120. All right, so if I'm looking at the different formulas I'm going to need, here where it's sloped, you're going to be using Q is equal to MC delta T. And when it's flat, there's no temperature change, so we don't have a delta T, so we're going to have to use a different formula. So here where it's flat, we're going to use Q is equal to delta H times the amount. We're just going to call the amount X. And then here it's sloping again, so we're going to use Q is equal to MC delta T. So we're using it here and here. Here we have a flat area again. So not only do we use this formula here, but we're going to use it here as well. And then for our last section, E to F, we're going to do Q is equal to MC delta T. We're going to have to add these 5 calculations together to get the total amount of energy. All right, so let's do that. So the first calculation that we're going to do is segment A to B. And this is for 20 grams of ice from -10 to 0, because that goes from -10 to 0. All right, so Q is equal to MC delta T. Our mass is 20 grams. Okay, so we need the specific heat of ice. So right here, C sub P of ice is 2.10 joules per grams degree Celsius. So our temperature is in Celsius and our mass is in grams, so we don't have to do any conversions there. Thank goodness. So 2.10, and the change in temperature is from -10 to 0. So it's that first segment, A to B. So that's a 10-degree change. All right, so multiply these 3 numbers together. So 20 times 10 is 200 times 2.10. Okay, so 200 times 2.10, 200 times 2.10. That's going to give us 4,200, or 4.2 times 10 to the 2, or let's move this decimal over 2 places. So that's 4,200. 4,200. So let me make sure, 4.2 times 10 to the 2. So I'm going to add some zeros here. 1, 2. Okay. Oh, it's 420. So I did have too many zeros. So see, it's always a good thing if you double check yourself. Okay. And that makes sense because 2 times 200 is 400. And then we're adding just this little bit. So 420. All right. So that's 420 joules. So this is how you catch yourself making those little bitty mistakes that get an answer wrong, is by being detail oriented and double checking your work. All right, so line segment A to B is 420 joules. And I have over here on this screen where I'm going to add them together. So segment AB is 420 joules. I'm going to go ahead and put that there. So now we need to calculate B to C. So that's that flat area of our graph, B to C. So I'm going to use delta H times the amount. So this is delta H for the heat of fusion, because it's melting at 0 degrees. So here it tells us the heat of fusion is 333 joules per gram. So 333 joules per gram. So we want our answer in, let's see, does it say? How much energy in joules? All right, so that's good. That already gives us joules, so we don't have to do a conversion. Because remember, sometimes it's in kilojoules, but this is in joules, so that's good. And we have grams, so we don't have to do any conversions. So this is good. We don't have to, so this is just 333 times 20, because all of our units match. All right, so let's go back to the calculator. 333 times 20. Okay, that's 6,660. 6,660. So let's go over here to this, 6,660 joules. All right, now let's calculate C to D. All right, so remember on our graph, A to B, B to C, so C to D. This is the liquid phase. Okay, so if it's the liquid phase, I'm going to be using Q is equal to MC delta T. So mass, 20 grams of water, times the specific heat for, now this is a liquid phase, so it's for water, so specific heat of water, 4.18 joules per grams degrees Celsius. So we're working with Celsius, we're working with grams, and we need our answer in joules, so we don't have to do any conversions here. So that's 4.18 times delta T. All right, so what is the change in temperature of the whole liquid phase? Well, 0 degrees Celsius is where we have water. So this melts to 0 degrees and it goes up to 100 degrees Celsius. That's the other place where it flattens out and starts to vaporize. So this change in temperature is from 0 to 100. So that's 100 degrees Celsius temperature change from 0 to 100. All right, so we just had 20 times 4.18 times 100. 20 times 4.18 times 100. Okay, and that's going to give us 8.36 times 10 to the third. 8.36 times 10 to the third. So what is that? Oops. One, two, three. So that's 8,360. 8,360 joules. Okay. So that's C to D. Now, D to E, that's where we have the flat part at the top. So A to B, B to C, C to D, D to E, this flat part. So we're adding energy. So this is going to be the heat of vaporization for water. And so that's right here. So that's 2260 joules per gram. And that's good. We have grams. This is in joules, which is what we want. So we're going to take 2260 times the amount, which is 20. We're going to get this section. So 2260 times 20. That's going to give us 45,200. So this is 45,200 joules. All right, almost there. So now we need to calculate from E to F. And so that's that point where it's steam. So this is 100 degrees. And what is our highest temperature? 120. So what's the change in temperature here? Delta T is equal to 20 degrees change. So since it's sloping, we have a change in temperature. It's MC delta T. The mass doesn't change. We still have 20 grams, right? Now we need the specific heat of steam. Now this is steam. So there it is right there. Specific heat of steam. 2.08 joules, which is what we want, per grams degrees Celsius. So we have grams in Celsius, so we don't have to have any conversions. So 2.08 times 20, which is our temperature change from 100 to 120. So 20 times 2.08 times 20. 20 times 2.08 times 20. That's going to be 8.32 times 10 to the 2. So 8.32 times 10 to the 2. Let's make this standard notation. So we're going to move our decimal 2 places. So that's going to be 832. So let's add that to our list. 832 joules. All right, now all we have to do is add this up, and this is going to be the total amount of energy that's needed to go from negative 10 degrees up to 120 degrees for water. All right, so 420 plus 6,660 plus 8,360 plus 45,200 plus 832. All right, so the total energy is 61,472. 61,472 joules. All right, now I want to show you something here. Which phase or which segment took the most amount of energy? And that would be D to E. All right, so D to E, this segment right here. Let's go back to our full curve right here, D to E. All right, look at that. It's the longest segment. Okay, so remember earlier in the video, I told you that D to E is the area that takes the most energy. We just verified 45,000, what was it, 200? 45,200. So for water, now remember this is just water, okay, H2O that we're looking at. For water, that segment requires the most energy. All right, so this is the longest type of problem that you're going to have where you have to do all three phases and the two phase changes. But say, for example, you might not have to go through all of those. So it says find the energy required to heat 35 grams of water at 80.1 degrees Celsius to 115. So let's look back, 80 to 115. And you might have to do this yourself to answer some of these problems. So 80 degrees is going to be here, and 115 is going to be here. So how many calculations are we going to need to make in order to solve this problem? The answer is 3, because we're going to need to make a calculation here where this line slopes here from this point up to D. We'll have a calculation where we have a phase change, and then we'll have a calculation from E to F, and this is for water. So for this particular question, we're going to have 3 calculations that we make and then add those together. So make sure that you understand that. Make sure that when you look at the questions that you're going to have for your practice problems, that you recognize where this is on the heating graph, the heating curve, and where this is, and then look and see what calculations you're going to need. So for our first calculation, it's sloping. So we're going to do Q is equal to MC delta T, because there's a temperature change from 80.1 to 100. 100 degrees Celsius is where the phase change happens. And then for the second one, Q is going to be equal to delta H times the amount. Now you have to make sure you get the delta H correct. And this is the top part of the graph at 100 degrees. So that's going to be the heat of vaporization. So you're going to go back and you're going to use this one, because this is the one that happens at 100 degrees. Fusion is the one that happens at 0 degrees. Okay, and then for the last one, again, it's Q is equal to MC delta T. Okay, and the temperature change is going to be from 100 to 115. Okay, so that's 15-degree temperature change. Okay, so on this one, it's going to be a 19.9 degree temperature change. We don't have a change in temperature here. Now, another thing that you're going to have to be aware of is here is liquid phase. Okay, here is gas. So the C is going to change. So for liquid water, it's 4.18. For steam or gas, it's going to be 2.08. Okay, so make sure that you see that you have two different numbers for that. Now, once you get this all calculated, you just add those together, and that's the total amount of energy that you need for this problem, those three segments. All right, so that does it. Let's make sure you slap that like button right across the face. Make sure that you click subscribe and notification bell so that you're notified when I put up example problems or other videos.